So now that you've seen pretty much all the code and we've visualized the implementation graphically and we've walked through the source code in quite a bit of detail, let's kind of take a step back and evaluate the pros and cons of what we've seen. So we're going to talk about the pros and cons of the search with sequential streams class and the associated methods that help out with it. So there's a number of benefits from this particular way of doing things using streams rather than using the object-oriented approach that we talked about before. Remember, we had that object-oriented approach that required a lot of manual steps, and you had to use looping constructs, and you had to allocate the various arrays explicitly, and so on and so forth. So one of the benefits with the streams version is it uses internal iterators rather than using the external iterators that we had talked about earlier, like a for each loop or an index-based for loop or a use of an iterator and so on. And there's a number of things that internal iterators get you that are really beneficial. The most important thing that they do is they help, well, one of the important things they do is they help to shield the programs and the programmers for all the implementation details of how streams work under the hood. So that's all hidden from you. Another nice benefit here is this pipeline is declarative, since it's a series of transformations that applied by the operations performed by the aggregate operations. So we kind of stream things together. Notice, in particular, we don't have to allocate any memory. That's all handled for us by collect, for example. In particular, we focus on what to do, not how it's implemented. We don't have control constructs here. We don't have allocation. It's just done, sort of from top to bottom. And I find that much easier to reason about. I can read it from sort of the beginning to the end and know what's going on. I'm creating a stream. I'm mapping things. I'm filtering. I'm collecting. I can read that in a linear pass from top to bottom, which makes things easier. Something that helps us in reducing the complexity is the fact that these behaviors we're seeing here have no side effects. So they are basically pure functions. There's no state that's stashed off to the side. They take some parameters, they do their thing, they return a result. And because of that, not only can you reason about the program better, because you just have to look at it and you don't have to go, oh, is there a hidden state somewhere that I have to keep track of that could be updated in ways that are inconsistent or get corrupted. So you can reason about your program better. And the other nice thing about having these stateless operations or these stateless behaviors in the intermediate operations is that we can have transparent optimization. In particular, we can go from a sequential stream to a parallel stream with just a little tweak to the code. And that's cool because it doesn't require changing the implementation. We just change the properties of the implementation, like is it parallel versus sequential, or do we pass in true versus false? And we'll talk about that when we talk about parallel streams. But of course, everything is not rainbows and unicorns. There are some downsides. The most obvious downside with this whole approach is that it doesn't take advantage of multi-core processors. So there is a single thread. After all, it's a sequential implementation. So there's just one thread of control. And therefore, despite the fact that we're running on a very, very powerful multi-core processor with all kinds of hyper-threaded cores, we perform like there was only one core. It's kind of like going back to the 1980s or something with a single core. So we don't really get any benefit from speed up of parallelism. And as you undoubtedly know, over the past decade or so, Moore's law has kind of petered out with respect to making processors run faster. Now we have more transistors, thus more cores, but a given processor doesn't run a lot faster. It's probably 3 gigahertz or so, and it's been like that for a long time. So that's unlikely to change anytime soon. So a single-threaded solution is clearly very limited. As we will see, maybe starting in a few minutes, when we look at the use of parallel streams, those implementations are much, much faster than the sequential version. The naive parallel stream version that just replaces stream with parallel stream gets us an over an n-fold speed up, where n is the number of processor cores, and the more aggressive form of parallelism that takes the input, a work of Shakespeare, and uses parallel splitterators to search for the phrases in each work of Shakespeare, that gives us an even bigger speed up. So we can make things run a lot faster if we parallelize things. Another limitation with this approach is it doesn't demonstrate the whole diversity of capabilities that come with Java. Streams just shows off a couple of methods. But having said that, and this is going to be really important when we talk about parallel streams, everything we've talked about in the course so far also applies to parallel streams. And it might seem funny that we're like almost halfway through the semester, and we really haven't talked much about parallelism at all, except for a few overview lectures at the beginning. But everything we've talked about is completely relevant for parallel streams. And that's the beauty of using functional programming in the way that Java 8 and other later versions do, that you can make these transitions without having to make any changes. Not surprisingly, there are lots and lots and lots of other operations that we haven't yet talked about, but we will talk about them, and we'll look at some other cool examples to make the point even more clear. And one of the really fun examples will be something called the image stream gang. And when we talk about parallel streams, first I'll show you how to upgrade the Sequential SearchStreamGang framework, SearchStreamGang we just looked at, to use parallel streams, a couple of variants of that. And then we'll talk about the parallel image stream gang example. And that is a very cool app that uses parallel processing to download, transform, store, and display images from websites. So it's a bit like your image crawler that you're writing, except in this app, you give it the list of images that you want to have downloaded and transformed. And whereas in the one you're working with right now, it goes and searches websites to find those images. So it's pretty cool, and we'll talk more about that later. Okay, so that's the end of the comparison.